Maybe you've noticed how often exponential functions come up in applications. It's a little bit strange when you think about it because, we're sort of used to dealing with polynomials and maybe rational functions. So why is it that something so crazy like exponential functions actually show up all the time? There are many situations where exponential functions show up, like here are just a few. Unconstrained population growth. So if you have some population that grows without any limit from the environment, typically it follows an exponential growth pattern. So the population at some future time is typically the population at some beginning time times e to the rt. Time is how much time has passed, and r is some number that measures how rapidly the population grows. So over time, you get an exponential growth in population like this. Radioactive decay is another situation where the mass of some radioactive sample, or the number of radioactive atoms in your sample, at some future time is some initial number of atoms times e to the minus rt, and t is the time, and r is some rate that describes how rapidly this particular radioactive material decays. The minus sign is what makes this decay instead of growth. And so in this situation, you're going to have something like this. Even though these two situations, one is growing and one is shrinking, you can see that both of these functions are just exponential situations. The only difference is whether your growth rate here is positive or negative, right? In a growth situation, it's positive, and in a decay situation, it's negative. Other examples are in cooling. So if you have some object that is either warming up or cooling down in some ambient environment, and the environment is large enough so that the temperature of the environment isn't appreciably affected by the temperature of the object that's warming up or cooling down, then the difference in temperature between the object and the environment at some future time is some initial difference in temperature times e to the minus rt, where t is the time, r is some rate of cooling or warming that typically depends on what the material is that's warming up or cooling down. And the minus sign just tells us that the difference in temperature between the object and its environment is getting smaller instead of bigger, which makes sense. That's how temperature works. So if you start out above the ambient temperature, the object is going to cool down. And if you start out below the ambient temperature, then the object is going to warm up. This is actually an interesting situation because in these previous examples, the negative part of your vertical axis doesn't actually make any physical sense. There's no such thing as negative population. And in the radioactive decay situation, there's no such thing as negative mass, at least not so far as we know. But for cooling, there is such a thing as a negative difference between the object and the temperature of the object and the temperature of its environment. That's just being cooler than the environment. But even with this new situation, exponential decay with a negative growth rate still describes the situation perfectly well. One final scenario that is described by exponential functions is in many interest and financial situations. So for example, if you have compounding interest, the amount in your bank account at some future time is the amount at some starting time times 1 plus some growth rate, typically sort of depending on how many times you compound per year, divided by k times kt. So the important thing about this is that all this stuff that I'm surrounding in brackets is a constant once you've chosen your interest rate and how often you compound. And so all of that stuff acts like some big constant that you're raising to a power. And again, it's exponential. Another way to write this is if you have, say, continuous compounding, or if you sort of relabel everything, then this looks like the amount in your bank account at some future time is the amount at some previous time times e to some growth rate times t. And so again, we get an exponential situation. So what is it about all of these that make exponential growth show up so much? There must be some sort of unifying principle that makes this, so I'll just use population as an example, there must be some unifying principle that makes this such a common scenario, right? It doesn't at first appear like all of those examples of exponential growth or decay. It doesn't seem like there's any unifying principle. They come up in such different situations that it's hard to know what exactly is going on. But now we have an extra tool that we can use to think about this sort of thing, and that extra tool is calculus. So just to see what we get, let's take the derivative of this with respect to time. So dp dt. And remember, this calculation doesn't really have anything to do with population in particular. This calculation would work just as well for any of the other examples of exponential growth or decay. So when we take this derivative, we get, let's see, this p naught just sits there. The chain rule spits out an r. So p naught r e to the rt. And our original population function is actually hiding here in the derivative. It's these two pieces. So if we wanted to, we could divide both sides by this stuff. So divide by p naught e to the rt, p naught e to the rt. So on the left-hand side, we get dp dt divided by, well, p naught e to the rt, that's the original population function. So we can write over p equals, and then the stuff on the right-hand side is just r. The only thing left is r, right? The p's cancel, the exponential part cancels. So this exponential growth scenario, another way to describe it is that this ratio is a constant. But what is this ratio? Well, dp dt, that's the rate of change divided by p itself, so that's the original value, is a constant. Remember, this r that shows up in our exponential growth formula is a constant. It's not a function of t, so equals constant. So another way to phrase this first equation is that the rate of change of something divided by its value is constant. And this is the key thing that unifies all of those different exponential growth scenarios. So for population, it kind of makes sense that the rate of change of the population divided by the size of the population is constant, because, right, for populations, what this is really saying is, if you have 1,000 people, they will reproduce a certain amount in a year. And if you have twice as many people, you'll have twice as many reproductions going on. So the relative size, or the relative rate of change, which is the rate of change divided by the original value, the relative rate of change is constant. This also makes sense for radioactive decay, because if you take the rate of change of the number of radioactive atoms divided by the original value, what you're really measuring is what is the probability that any single radioactive atom will decay in one time period. But since all of those radioactive atoms are the same, that ratio is going to, or that probability is going to be a constant. And it's the same for the other examples of exponential growth and decay. There's always some sort of sensible reason why this ratio, which is the relative rate of change, should be a constant. And whenever you have a relative rate of change constant, you get exponential growth or decay.